Good afternoon, students, friends of BSc 4th semester. Today, I will discuss with you a Poyinting theorem, and this Poyinting theorem happens to be the last article of electromagnetic theory. This is also known as Poyinting vector, Poyinting theorem or Poyinting vector. It is Poyinting theorem or Poyinting vector. Poyinting vector. So its proof, its statement, and how this energy of electromagnetic wave propagates. It gives us an idea about how the energy is propagating. So statement, let me write statement, or let me state the statement. It states that the Poyinting theorem states that in a plane electromagnetic wave, other day we have derived the equation for plane electromagnetic wave. The rate of flow of energy through unit area. In a plane electromagnetic wave, the rate of flow of energy through unit area is proportional to the vector product of electric field and the magnetic field intensities. I repeat, this Poyinting theorem is stated in a different forms with a different statements. You can say Poyinting theorem here we can state in a simple way. It states that in a plane electromagnetic wave, the rate of flow of energy, through unit area is proportional to the vector product of electric field intensity and the magnetic field intensity. To explain this, when electromagnetic wave travels or propagates from the source, there must be a source of electromagnetic wave. Say a bulb is glowing, 100-watt bulb, or here the tube light is glowing. We have said the electromagnetic radiations are nothing but light radiations. They are in the different, say, frequency ranges. Fine. Electromagnetic wave travels from the source to a point under consideration, source to point in a space. Here is a source and here is a point. Through the space, it transfers the energy from the source to the point under consideration. The rate of transfer of energy can be expressed in terms of electric field intensities, the electric field intensity and the magnetic field intensity here. Hope you got this. Poyinting theorem or a Poyinting vector here gives us an idea about how does the energy is carried by electromagnetic wave. We have seen the equation that is in a free space, and that too in a plane electromagnetic wave. Why I am saying here a plane electromagnetic wave? Because the wave may be polarized also. A plane polarized wave, elliptically polarized wave, and so on. So we have concentrating on plain polarized electromagnetic wave. Rather, we have not considered polarization factor here. We set here a general plain electromagnetic wave in a free space. That may be in a different mediums also. Other day we have discussed it. To derive this, or to prove, or to derive the equation for this theorem, whatever we have stated, that should be proved here. To derive the Poyinting theorem, let me start from this point. I'll write, we have derived Maxwell's equation. Point here, please remember. Students, please remember here, we are deriving this Poyinting theorem or a vector using Maxwell's equation. There are other methods are also available. We should use this as an application of Maxwell's equations. Let us consider equation number, say 4, del cross H is equal to J plus dou D by dou T. This is equation number 4. That is Maxwell's equation. I will write it as equation number 1. Let us consider equation number 3. That is del cross E equal to, say, minus dou V by dou T. I will call this as equation number 2. Now the equation 4 and 3, here I have called it as equation, say, 1 and 2 to obtain Poyinting theorem or to prove the Poyinting theorem. Let us take a dot product on both sides of these equations, equation number 1 and 2. The dot product with E, the electric field intensity, and magnetic field intensity. Taking the dot product both sides of equation 1 and 2 with E and H. Let me take with E dot del cross H. It's a curved product here, that is equal to E dot J plus, say, E dot dou by, say, dou D by dou T. This I can write it is equal to, as it is, E dot J plus, I will take this partial derivative outside, dou here plus dou by dou T into bracket. Say, I will write it as D. I know this D is equal to, we have used epsilon naught E. D is equal to epsilon naught E, and here E, I will write this is half epsilon E square to make it mathematically simplified. Say, I will call this as equation number 3. That is, this is equal to this term here. I will take the del, that is dot product with equation number 2 with H dot del cross H. Okay, it is equal to H here with this dot minus dou V by dou T. This I will write it is, this side I will write it is equal to, taking minus sign out, taking dou by dou T out, and I will write this V here, V is equal to mu H. Okay, so V is equal to mu H, and H I will write again half mu H square. This is, and I will call this as equation number 4. We got equation 3 and equation 4. We got it from these two Maxwell's equation. Subtracting this equation 4 from equation 3. Subtracting equation 4 from equation 3, I will get, that is E, say dot del cross H minus this term H dot del cross H, which is equal to this term, that is this E dot J plus dou by dou T. This minus, okay, subtracting. So here I'll write in brackets, that is first quantity this, because it is plus half mu H square minus of man, this becomes plus here. Okay, that is half epsilon naught, say E square. This is equation number 5. Now we are dealing with this quantity, that is LHS. So from vector identities we can show that, or we can show that, say dot product and cross products are interchangeable. Dot and cross products are interchangeable. So using this part minus del, I can show this E cross H. We are interested in this. We have come across in a statement this, that is equal to, say H plus H dot del cross E minus E dot del cross H. This is now this can be written as, okay, this side we got this is, so this is equation number 5. The LHS is replaced by this, that is therefore del dot E cross H, we are taking only this, that is with minus sign here, which is equal to this, that is E dot J plus dou by dou T into bracket half mu H square plus half epsilon naught E square. Many times in physics, whenever we want to get half mv square, a energy term, we go for this simplification term like this, either here or here or here, you can say. Now I want to integrate this, give some physical meaning for this. Let us consider a volume V enclosed by the surface S. Enclosed by the surface S. This equation we can integrate, equation number, let me call it as equation number 6. Integrating equation 6 over the volume V. So I'll write this in a different manner. Dou by dou T integral for the volume V mu H square upon 2 plus epsilon naught E square upon 2 dV plus this term, integrate it for volume V, this is V E dot J dV, which is equal to the other side minus, say, integral for the volume V del cross del dot E cross H. E cross H d. Let me call this as equation number 7. Once we get this, using Gauss divergence theorem, I will convert this volume integral into surface integral using Gauss divergence theorem. Let me convert that is volume integral. Not here, the volume integral is converted into surface integral. Del dot E cross H dV is equal to, by definition or using this theorem, it is converted into surface integral, closed surface integral. E cross H ds. So when we got this, we consider a volume enclosed by the surface S. Integrating this equation over the volume, we got 3 integrals with the rearrangement. I want to convert only this integral into surface integral. So we got this. I'll rewrite this equation now. Therefore, that is dou by dou t, that is this integral over the volume V, that is half mu h square plus half epsilon h square dV is equal to, or you can write it is minus, taking this E dot j to minus, say minus for the volume V E dot j dV, taking this as minus. Okay, taking this as minus here, you can say this is plus to make it here surface integral, that is E cross H, and this is equation number 8. Now look at this equation number 8. Each term has certain physical significance here. This is LHS of the equation. After rearranging this, we got it here minus dou by dt. This sum of this, that is integral over the volume V. The LHS, the first term on the LHS of equation 8 represents the rate of decrease of energy stored in the volume V due to electric field and magnetic field here. E and H are electric and magnetic field respectively. The first term on the LHS of equation 8 represents rate of decrease of energy stored in volume V due to electric and magnetic fields. The second term here, volume is, that is energy stored in a volume V, and the rate of decrease of energy stored in a volume V due to electric and magnetic field. That's first term. The second term here indicates, that is the loss of energy due to joules heating. You know that when there is a source of energy, say it gives the energy or delivers the energy here, and that energy propagates to the point under consideration from source to point, While doing so, there will be a loss of energy due to Joule's heating. And many a times in physics we have come across this kind of situation, and that is equal to the RHS term represents the rate of flow of energy over the surface S including volume V. This side, the term on the other side of equation A represents the rate of flow of energy over the wall or the surface enclosing volume V. Now here, to say something about this, the equation number 8, in that we got what is called as E cross H. E cross H, and this term E cross H gives us the rate of flow of energy through unit area enclosing volume V. That is this E cross H gives us the rate of flow of energy through unit area enclosing volume V, and this is represented by vector P, called as Poyinting vector. I can write P is equal to E cross H. E is electric field intensity, H is magnetic field intensity, and the cross product of these two is a vector, and that is known as a Poyinting vector. What about the direction of this? E is vector, H is vector, P is also vector. What is the direction of vector P? This vector P is called as Poyinting vector or a Poyinting theorem. The direction of this Poyinting vector P is perpendicular to both E and H. E and H. Direction of E is direction of P is perpendicular to both H and E, you can say, or E and H. So we rewrite this equation now. Equation number 8 can be rewritten here. Let me write that once again on whiteboard here. So volume integral E dot J. We have this dV on that side. That is equal. I got this. I have taken this as here plus. I will take it as plus only. That is equal to minus dou by dou t. Write the volume integral. That is mu h square upon 2 plus epsilon E square upon 2 dV minus say or S surface closed surface integral E cross H ds. Rewritten this equation number 7 or equation number 8. Now this indicates here the time rate of change of electromagnetic energy within the volume. This term indicates the time rate of change of energy within a certain volume V plus, say this you can say, time rate of change of electromagnetic energy within a certain volume V plus the time rate of energy flowing out through that volume, okay, or through that surface S here, boundary surface, is equal to the power transmitted to the electromagnetic field. This is another statement of this Poyinting theorem. Either you can state here, that's good, or getting this equation you can state the Poyinting theorem. Now what is this Poyinting theorem or a Poyinting vector here? Poyinting vector, okay, the rate at which the energy is transmitted through unit area perpendicular to the direction of propagation of energy is called as Poyinting vector. Many times they ask it as Poyinting vector. P is equal to E cross H, and you have to say this same thing in words. That's all. So let me repeat here. Poyinting vector, the rate at which energy is transmitted through unit area perpendicular to the direction of propagation of energy is called Poyinting vector. Let me solve a simple example based on this. This has been asked in a previous examination. Okay, so I'll take that. Calculate the value of Poyinting vector for a 100 watt bulb. 100 watt bulb at a distance, you can take any distance 1 meter. This was asked for 2 marks from it. That means here is a bulb, here is a bulb, this is a bulb, okay, and this is 100 watt bulb. Its power rating is known, and here is a point P at a distance 1 meter. 1 meter. I want to calculate the Poyinting vector at this point, and this can be done. The average P average power, that is Poyinting vector. So we got this average power is equal to 100 watt, and energy flowing per unit area, that is power, you can say P average is equal to, say here it is P by 4 pi r square, or r is 1 meter. That is the distance from it. So if you simplify this, that is 104 into 3.142 into 1 square. So this will be, say if you calculate this, this will be 7.98 watt per meter square. And this is how we have defined the Poyinting vector. So, or a statement of Poyinting theorem. In an electromagnetic wave, the rate of flow of energy per unit area or through unit area is directly proportional to the product of electric field and magnetic field. So we can calculate, because the power is given, we have calculated at this point the Poyinting vector, the value of Poyinting vector. Student friends, I have completed this electromagnetic theory. Somebody asked me what is the weightage for this topic. It is 8 hours. So you can calculate 1 hour. So approximately what will be the questions on this if they conduct the examination? 10 marks question on this. Say 5 mark question on this, and say 1 or 2 marks. 2 into 2, let us say 4 marks. So total 10, say 5 plus 4, 19 marks on this maximum. So the weightage will be around 19 marks on this topic out of 1, say 24 in total question paper. So apart from this, what I was supposed to teach is interference, part of interference. I will start that in the next class, that is Michelson-Morley interferometer. Already you have studied the interferometer from the other person, other teacher here. My colleague have taught you interference up to Newton's ring, and the next continuation of that is Michelson interferometer, its construction, its design, its working, its little theory. It's very good quality equipment. It is Michelson interferometer. For a new syllabus, they have introduced it. If say the college provides that, we will establish that equipment in the laboratory. Not this year, at least for the next year. And we can study using that determination of wavelength of monochromatic light, what we do using biprism experiment, using Newton's ring experiment. Many more things can be studied using Michelson interferometer. The important application is to find the fringe width, and then calibration of your meter scale is mentioned in your syllabus. We'll do it in the next few weeks. Alright, so thank you for this.